Let's do another continuous charge distribution problem now. Let's take our line of charge and let's form it into a ring with radius r. So from here to here is r the radius. So this will be partly new. We'll find the electric potential at point P due to this ring of charge. And then we'll do a refresher from Physics 1051, which is if you have an electric potential, how do you find the electric field? So we'll take our time and go through that. We'll use the result for the ring to find the electric potential of a disk, and then we'll find that expression for potential to find the electric field of a disk and compare it to what we know from before. So to get started, we're going to use our same approach. First thing we do is we identify some small piece of charge dq. So we'll color that in, we'll label it dq. Remember, potential is a scalar, so we're not drawing a vector here. So dq makes a small amount of charge at point P. Hang on, I think I missaid that. dq makes a small amount of potential dV at point P. That small amount of potential dV is k times the charge dq divided by the distance little r. Be super careful with all the r's here now in this problem. Little r is the distance between the charge and the point we're talking about. This r right here from charge to point is the hypotenuse of a right angle triangle where the legs are the z coordinate and the radius of our ring. So I originally drew my arrow for r right here. I could just as well have drawn it from right here because it goes from the center to the perimeter of the ring. That means that the distance between dq and p is the square root of the radius of the ring squared plus our z coordinates squared. We're trying to find the electric potential somewhere on the z-axis. Okay, so now let's start finding our potential. So our total potential V is the sum of all the contributions, dV. So that's going to be the integral of k times dq divided by the distance between the point and the bit of charge, which is the square root of the radius of the ring squared plus the z coordinate squared. Our constants come out front. K is a constant, radius of the ring is constant, and that z distance is constant. So we're left with the integral of dq. Maybe you remember this bit from when we did our electric field of a ring. The integral of dq is just the net charge on the ring, q. Okay, so that gives us a result that our potential at point P, which is a distance z along the z-axis, is equal to k times the net charge q divided by the square root of r squared plus z squared. Okay, that's our potential due to this ring. Let's take this answer now and let's build on it to find the potential of a disk. So next we're asked to use the expression for the net potential due to a ring to find the net potential due to a disk. You might remember that we did this sort of thing with electric field, and we're going to follow those same steps here. So first of all, I know that to find my total potential, I need to add up all the little bits of potential due to all the little bits of charge dq. So I have to pick a dq. And I have to pick a dq so that overall it will add up to give me the total disk. Well, if I look at a whole set of concentric rings, and I take them all the way from the center all the way out to the perimeter, then that set of rings would add up to give me the whole disk. So I'm going to say that a disk is the sum of a set of rings. So for my dq, I'm going to pick one such ring, and I'll draw it here. I'm going to shade it in because that's what we do in all of our other examples. We identify our dq and we shade it in. So for my disk, it's a sum of rings. Our ring has charge dq. And makes potential dV. So the little bit of charge makes a little bit of potential dV. Okay, let's just make sure we understand the nature of our disk and our rings. For our whole disk, I'm going to use capital R for the radius. For the distance between dq and our point, I'm going to call that r. That is the typical notation. So from here to here, That's a lowercase r. For the radius of my ring, I don't want to use r again, so I'm going to choose to use a. So the radius of my ring is a. The thickness of my ring, or the width of the ring, is going to be a little bit in the a direction, equals dA. So my ring has charge dq, it has radius a, and it has thickness dA. Okay, let's start to put this together with what we did on the last slide. Our net potential is going to be the sum of the little potentials. We found the expression for the potential of a ring on the previous slide. Let's go back and write that down. I've copied a picture of our result from our ring here on the top, and below I've got a picture of what we just did from our disk. So this is the potential due to a ring of charge. Let's write this potential in terms of the notation in our bottom part. So in our bottom part, our ring of charge has potential dV. So why don't we get an arrow just to make sure we're all clear here. dV is the charge on our ring. That's the notation we've adopted right here. That's equal to our Coulomb's constant K. That thing doesn't change. Times the net charge on the ring. The net charge on this ring is what we called dQ. Divided by the square root of the distance between the ring and the point where we're trying to find the potential. Okay, so that distance r in this picture down here, this r is a hypotenuse of a right angle triangle where the legs are z and the radius of the ring, which is a. Okay, so just to recap, dq is the net charge on our ring from this picture. dV is the net potential created by this ring. R is the distance between the ring and the point, and that's given by the radius of the ring squared plus our coordinate z squared. Okay, so now we know to get our net potential, we have to sum up all the contributions due to every single ring. So that's going to be the integral of k times dq divided by the square root of a squared plus z squared. Thinking about our integration now, we can certainly take our constants out front. K is going to qualify. A, however, is not going to be a constant because we're summing up due to every ring, and the rings will have different radii. Okay, that's the first thing. So the A can't come outside. Next, we have to deal with our dq. When we have a linear charge density, we say that dq is the linear charge density lambda times the length. We have a surface area here now, so that means for this case, our amount of charge on our two-dimensional ring is going to be the area charge density times the area. So it's always the density times the size parameter. Our charge density has a symbol of sigma, so that's the charge density of the entire ring. And then we'll just put that on the side. So sigma would be net charge divided by net area. So that would be the total charge on the ring is Q. The net area of the ring would be 4 pi r squared. Okay, so there's the charge density. Back to our dq, it's our charge density sigma times the area of our ring of charge. How do we find the area of the ring of charge? Okay, so hopefully you remember when we did this in our electric field, and I had a model made out of pipe cleaners. If we can take our little ring that has area A and we can unroll it. If we unwrap it and unroll it, all of a sudden it looks like a long rectangle. And the dimensions of this rectangle are the length, so the length all around the circle, which is 2 times pi times the radius. And the width of our rectangle is the same as the width of our ring, which we called dA. So the area of our ring is going to be length times width, or 2 pi a times dA. dA. Okay, I think we have a lot to put together here now. So let's put this expression in for our dq, and then let's carry on with our integral. Let's carry on with our integrating now. So V is equal to the integral of K times dq, but dq is equal to sigma times 2 times pi times a times dA. And then that has to be divided by the square root of a squared plus z squared. So we're going to be integrating with respect to a, the radius of each of those individual little rings. Let's take our constants out front. Coulomb's constant is constant, charge density of the ring is constant, 2 is constant, and pi is constant. So now we're outside the integral of a times dA divided by the square root of a squared plus z squared. We need to put in limits of our integral, so we're integrating with respect to a. A starts at the center, a little tiny ring at the middle, so it begins with a equals 0, and it stops with a ring out at the outer perimeter, so a equals capital R. So our initial value of a is 0, our final value of a is capital R. So the integral of a over a squared, square root of a squared plus z squared, v equals sigma 2 pi. That integral is equal to the square root of a squared plus z squared, and that has to be evaluated at r and 0. So let's put in those numbers. V equals k times sigma times 2 pi outside of the square root of r squared plus z squared. Subtract the square root of 0 squared plus z squared. The square root of z squared, that's just going to give us 0. And that gives us a result of v is equal to k times sigma times 2 pi outside of the square root of r squared plus z squared minus z. So there's our net electric potential due to a solid disk of charge. So now let's go through part C, which says use your answers to A and B to find the electric field of a ring of charge and of a disk of charge. So here's our answer to part A. This is the net electric potential at point P, which is a distance z on the z-axis, or from the center of the ring. We want to find the net electric field of the ring from using this equation, not from integrating over the ring, but from this equation. So we're asked to find the electric field. So as a reminder about how to do this, we know that electric potential is the integral of electric field with respect to the path taken. This comes from remembering that electric potential energy is negative of the work done, and the work is F dot ds. Okay, so that was your first step in finding this result. The next step in this result is knowing that delta V is delta U, the potential energy, divided by the charge. That's what leads to this result right here. Okay, so if you had the electric field, you could do the integral of it to find the potential. In general, that tends to be a bit tough. The flip side, however, is less tough. If we know the electric potential, we can find the electric field. So since potential is the integral of electric field, then electric field is the derivative of electric potential. So electric field is derivative of potential. The hitch for this bit is potential is a scalar and electric field is a vector. Okay, that bit's pretty important, but how do we go from the derivative of a scalar to get our answer that's a vector? Well, the answer to that question is that the electric field is a special kind of derivative, and that derivative is called a gradient. So it's minus del, that upside down triangle with the arrow is called del, and that means the gradient. So it's minus the gradient of the potential. Okay, what that bit means is that the x component of electric field is the derivative of the potential with respect to x. Okay, and these symbols here, they're called di v by di x. That means the partial derivative of v with respect to x. I expect you've seen that in a math class, but we'll talk about it as we go through. The y component is the partial derivative with respect to y, and the z component is the partial derivative with respect to z. That gives us the x, y, and z components of our electric field, and then we just write our electric field vector in the usual way. Okay, so here's our strategy. We're going to take the derivative of this expression with respect to x, we're going to do it with respect to y, and we're going to do it with respect to z. That's going to give us our x, y, and z components, and we're going to fill those components in to write our electric field vector. Okay, let's start with the x component. The x component of the electric field, Ex, is negative the partial derivative of the potential with respect to x. You might know this before we even get started. Feel free to skip ahead a tiny bit if you're already familiar with this. So it's minus di by dx. I'm going to fill in now my expression for my potential for my ring, which is k times q divided by the square root of r squared plus z squared. Okay, here's where we talk about what the partial derivative means. It means we take the derivative of, we want to know how this expression changes with respect to x. So we take all of these things as constant and we do the derivative with respect to x. So all of these things do not depend on x. They don't change with x, which means they are constant with respect to x. So constant with respect to x. So taking the derivative of a constant gives us 0. Okay, and that makes sense due to the symmetry considerations. The x component of the electric field is the bit that goes back and forth here parallel to the x-axis. The net amount of electric field from this side of the ring in the x direction will cancel with the x component from this side of the ring. So we anticipated that the x component of the electric field would be 0. Okay, what about the y component? Let's do that one next. Ey equals minus di v di y, which is minus di by di y of k times q over the square root of r squared plus z squared. Okay, this one has no y dependence. This one is constant with respect to y. That means the derivative of this with respect to y is also 0. Totally makes sense. The electric field from the top half of the ring, the y component will point down. The electric field from the bottom half of the ring, the y component will point up. Those will cancel and we'll be left with a 0 y component. Okay, that leaves us with finding the z component. For our z component of electric field now, the z component is minus the derivative of the potential with respect to z. So minus di by di z of k times q over the square root of r squared plus z squared. I can take my constants out front, minus k times q di by di z of 1 over the square root of r squared plus z squared. Okay, I'm going to do one little bit right here, just because I find it makes it easier to do the derivative. I'm going to write this as r squared plus z squared to the minus 1/2. Okay, so that means that my Ez then is equal to minus k times q times the derivative of r squared plus z squared to the minus 1/2. It's just a power law derivative. So that's minus k times q. First of all, we multiply down the exponent, minus 1/2. Then we multiply by the thing inside. The thing inside has its exponent reduced by 1, so that's to the minus 3/2. Then we multiply by the derivative of the stuff inside. The derivative of r squared is 0 because it's constant. The derivative of z squared is 2z. Okay, so if we look at this, minus times minus gives us a positive. 2 divided by 2 gives us 1. So then our result for Ez is equal to k times q times z over r squared plus z squared to the 3/2. Okay, so now our very last thing we have to do is write our answer as a vector. Writing our result as a vector then, our x component is 0, y component is 0. So we've got our z component, and that has to be written in the z direction. If you go back to our electric field notes, you'll see that this is the same expression we found when we found the electric field at this point by integrating over the ring. So a little tip I would give you here, if you're doing a problem and you ever have the opportunity to do an integral to find your potential and then a derivative to find your electric field, I would probably recommend that you do that method every time just because it's a little bit easier. It's a little bit more straightforward than jumping into the integral to find the electric field. Okay, next part of C is to find the electric field due to a disk. Okay, let's do that approach again, but now we'll use the expression for the potential of a disk. We'll take the gradient of it and we'll get our electric field from a disk. So we know right off the bat that our x component, so why don't we even write that down? So our electric field is minus the gradient of the potential. It means that our x component is minus di by di x of the potential, which is minus di by di x of k times sigma times 2 pi times the square root of r squared plus z squared minus z equals 0. There is no x dependence, so the change with respect to x is 0. Okay, likewise for our y, we can probably zip through that pretty quickly. That's also equal to 0. The potential doesn't change with respect to x or y, so the x and y components of field is 0. Okay, that leaves us with the z component. Ez is minus the derivative of the potential with respect to z, so minus di by di z of k times sigma times 2 pi times the square root of r squared plus z squared minus z. Finish off our brackets there. This slide is already full, so we'll spill on to the next one. So for our next bit of our integral, we'll take our constants out front. Ez is minus k sigma 2 pi times the derivative with respect to z of the square root of r squared plus z squared minus z. So since we're subtracting these two terms, we can break that derivative into two bits. Ez equals minus k times sigma times 2 pi times the derivative with respect to z of the square root of r squared plus z squared minus the derivative with respect to z of z. This gives us Ez equals minus k times sigma times 2 pi times the derivative of the square root of r squared plus z squared is going to be 1/2 times r squared plus z squared times 2z. And then the derivative di z by di z is just 1. Okay, this is coming together. I notice I've got a 2 here and a 2 here, so they cancel. I know that K, my Coulomb's constant, equals 1 over 4 pi epsilon naught. And I'm going to multiply my negative sign in through. Okay, let's see where that gets me. Ez equals K, oops, sorry, look, I already left something out. K, which is 1 over 4 pi epsilon naught, times sigma times 2 pi times minus z over the square root of r squared plus z squared plus 1. So I've multiplied my minus sign in here. A little bit more cancellation. Pi cancels with pi. This 2 goes into this 4, leaving a 2 on the bottom. So now our final result for Ez is equal to sigma over 2 epsilon naught. Oops, I said 2, but I wrote 3. 2 epsilon naught outside of 1 minus z over the square root of r squared plus z squared. Okay, to finish now, all we have to do is write our answer as a vector. So for our final result, our electric field vector doesn't have an x or a y component. The z component is sigma over 2 epsilon naught, 1 minus z over r squared plus z squared, square root there in the denominator, in the z direction k hat. And if you go back to our section on electric field, you would see that this was exactly the same result. Okay, here's a bonus theory question, and I like to throw these at you once in a while because these are the kind of questions I may well pop up with for a test. Back when we talked about electric fields, to find the electric field of an infinite plane, what we did was we came to this result for the disk, and to find the plane, we said the plane was a disk as r goes to infinity. And we did that bit when r went to infinity, this whole term went to 0, and our electric field of a disk was sigma over 2 epsilon naught. That's how we found the field of a disk. It was constant and it pointed straight out from the disk. If we tried the same approach with the electric potential, we would see that if we took r going to infinity, the electric potential would also go to infinity. So why does the electric field stay constant, but the electric potential blows up? Is that something maybe you could think about? See if you can come up with an answer.